welcome back. So, let us continue from where we left off. The third property of the generating function is given in the red box at the top of the slide, and this is the expression that was given for the generating function, and this has the solution and given in the green box of the slide. That is what we have to establish. We have to establish the solution for the equation that is given in the red box at the top of the slide. The top of the slide contains the equation and the green box contains the solution, and we have to establish the validity of the solution. So, we start by inserting the solution into the equation that is given to us. On inserting the solution, this solution which is in the red box at the top of your slide, which is in fact here also in the in this expression, and we substitute this in the green box, which was the equation that is given to us and that we in fact derived earlier. And please note, as you will see in the next slide here, we introduce an expression O as the operator, which is equal to I integral this whole thing. So, E of O is equal to E of exponential of the expression that is given in the square bracket and in the red box in the top of the slide. In other words, we have substituted E O as exponential of the square bracket that is there in the top of your slide. So, we can write Z j as E O Z0 j. This clearly originates from the expression that we have for Z j. Z j is equal to this expression into Z0 j. We have already established it in the previous lecture a number of times. So, Z j is equal to E of E O into Z0 j. Then we have on operating with the Kleene-Gordon operator, box plus m square into del by del j x minus L integral this into Z j will give us what? It will give us E. In other words, we are starting with the left hand side now. If you look at this, let us go back. This is, we are now starting with the left hand side of this equation. Box plus m square del Z j upon del j x, del Z j upon, that is precisely what we have. Of course, we have now introduced this term minus L dash integral this expression into Z j. This has been obtained by substituting the solution into the original equation as we go back in the previous slide. This is equal to this expression. So, if we take this to the left hand side, I will get this expression. Now, let us look at what we get from here. Z j, as I mentioned earlier and as is shown in the red box given at the top of your slide, is nothing but E O Z0 j. We write it as E O Z0 j, and then we argue at a later point immediately after this that E O commutes with whatever is there in the curly brackets, and therefore, it can be taken to the other side of the curly brackets and can be written in the form that is given in the green box at the bottom of your slide. Now, to establish, we need to establish that E O commutes with the terms that are appearing in front of it in the expression given in the green box, in this expression in the curly brackets in the blue box at the right hand side of the blue box at the middle of the slide. So, E O is equal to this expression by definition, that is what we have substituted. Now, we can see the interaction Lagrangian can be written as a power series of the derivative operator of the functional derivative of j x, as a power series of the functional derivative of j x. Now, the commutator of the functional derivatives j x and j y at commutators, the functional derivatives at point x and point y do commute with each other. And that means what? That means that every term in this exponential commutes with the functional derivative of Jx. Let us go back now. So, what we have established now is that this E of O commutes with del of del Jx, that is one part we have established. Now, as far as the Kleene-Gordon operator is concerned, it consists of ordinary derivatives, and therefore, E of O also commutes with the Kleene-Gordon operator. That is also, so it commutes with this term del of functional derivative of Jx, and it also commutes with box plus m square. And remember, we have written L interaction, that is the interaction Lagrangian, as a power series in the derivative operator. Therefore, L dash of the interaction, the derivative of the interaction Lagrangian will also be a power series in the functional derivatives of Jx, and therefore, E of O will also commute with this term, the derivative of the interaction Lagrangian. So, it commutes with all the terms in the curly brackets, and therefore, it can be taken to the left hand side of the equation. So, that is where we have now. And now, for the free field, what do we get? For the free field, we have from the previous property that we have derived, the expression that is given here, 1 upon I box plus m square del of z0 upon del Jx is equal to Jx z0 j. So, we substitute this in the first term on the curly brackets in the previous equation. So, what do we get? When you substitute from this, after transposing the Kleene-Gordon operator to the right hand side as its inverse, when you substitute this here, what we get is the expression that is given in the yellow box, and this expression in the yellow box now gives us Jx, the box plus m square and its inverse cancel each other, gives us the delta function, gives us the unit function, and Jx remains as it is, z0 j remains as it is, z0 j is taken common and taken outside the integral. The second term remains unchanged, and E0 at the beginning at the left hand side is also unchanged. So, what we have simply done is we have used the expression for the free field here, the expression that is there for the free field, and we have, using this expression for the free field, we have substituted for del z0 j upon del j in terms of the inverse of the Kleene-Gordon operator, and that inverse of the Kleene-Gordon operator cancels the Kleene-Gordon operator here, and giving us only Jx as the first term within the curly brackets. The second term we have not disturbed so far. Now, let us see what happens as far as the second term is concerned. As mentioned earlier, we write L interaction as a power series in terms of the functional derivatives, as sum of the power series in sum of the functional derivatives as the expression in the red box. And now, the commutator of each term of the series with Jx can be found by using this identity. This identity is straightforward, it is easy elementary to prove, and this identity in the green box here will be used for commuting the higher commutators of this expression. For example, we have for the second commutator n equal to 2, we have the expression in the red box gives us on simplification the expression in the blue box, and in general what we have is the expression here for the nth commutator or the nth power of the functional derivative commuting with Jx gives us the expression that is given in here in the right hand side of equation in the green box right at the bottom of your slide. So, from this what do we get? We get the commutator of O and Jx. Now, O is written as this, you see, e to the power o was written as e to the power this expression, e to the power integral d for y L integral this expression. So, o was equal to this expression which is here, and the left hand side expression in the commutator j is retained as it is. Now, we have written L integral as a power series in the form which is shown in the blue box in the middle equation on the slide. And now, we have the commutator of this expression, this expression within the round bracket with j x as giving us the delta function here together with 1 power less, that is n minus 1 with sigma n, and if you integrate it over y, the delta function goes away with the substitution y is equal to x, and we also have the expression which is within the summation. If you look carefully, the expression within the summation is nothing but the first derivative of L interaction. If you write, let me reiterate, if you write L interaction in the form of the power series which is shown in the blue box here, then the expression that you get in the green box here is nothing but the first derivative of L interaction. But our requirement, if you look carefully, is e to the power o j x. If you look at it here, let me go back, e to the power o j x, that is what we need. We do not need o j x, we do not need the commutator between o and j x, we need the commutator between e to the power o and j x. So, we still have some work to do. Now, we consider or we make use of the Baker-Campbell-Hausdorff formula which is written in the form given in the green box at the bottom of your slide, the Baker-Campbell-Hausdorff formula. Now, the important thing here is that in our case the double commutator vanishes and therefore, the series terminates. If we write A equal to j x and B equal to O, we have A B is equal to j x comma O, which we have already found as equal to I L dash. Please note, it is not L, it is L dash. We found it here. Let me go back. Yeah, this is the expression O j x, the commutator between O j x is equal to 1 upon I this expression. Therefore, the commutator between j x O is minus of this, which gives us this expression. Now, since L interaction is represented as a power series in j x, therefore, L dash interaction is also a power, consists only of derivatives of j x, a power series of j x, of derivatives of j x, it consists of power series of derivatives of j x. Let me repeat, L interaction consists of power has been expanded as power series in derivatives of j x, functional derivatives of j x. Therefore, L dash interaction will also consist of power series of derivatives or functional derivatives of the form del upon del j x. Now, these derivatives commute with each other, therefore, and j x comma O is equal to L dash j. So, L dash j and O, because O consists of only derivatives of j x, L dash j consists of derivatives of j x, therefore, they commute with each other and we get 0. So, the series terminates, and therefore, what we have is j x e to the power O is equal to e to the power O j x plus e to the power j x comma O, which is equal to e to the power j x plus I e to the power O L dash integral, where we have substituted the value of this commutator here. Now, if we multiply throughout by z 0, because we want z j, so j x e to the power, no j x, we want j x z j. So, we multiply throughout by z 0 j. Multiplying throughout by z 0 j, we get the result which we were required to prove. Now, we come to Schwinger-Dyson equations. Schwinger-Dyson equations in the context of the phi 4 field in the Minkowski space. So, the action of the field can be written in this form which is in front of you. We have already discussed that after a integration by parts, it can be put in the form that is here in the red box, and the coupling constant has been retained as lambda 4. We are talking about the phi 4 field. So, we have a phi 4 term in the action. The generating functional then takes the form that is given in the red box in the slide, and that can be written as exponential Wj, where Zj is the generating function of all green functions and Wj is the generating function for the connected green functions, and Jx is the source of the field. The effective action is given by the Lagrange transformation of Wj, and it can be written in the form that is given in the red box in the slide, and it depends on the average field capital Phi in the presence of the source J. And in particular, the effective action generates the green functions, one particle irreducible green functions, 1 pi green functions, which are a subset of the connected green functions, and the field functions is a derivative of Wj and can be written in the form that is shown in the red box at the top of the slide, and that can be simplified and put in the form of the green box that at the bottom of the slide. And the current is also a derivative of the effective action. Look at this, the field function is a derivative of Wj. Please note this, Wj with respect to Jx, field function is the function of the Wj, that is the generating function for the connected green functions with respect to Jx, and the derivative of the effective action with respect to phi j, capital Phi j, which is the field function, gives us Jx. The endpoint functions are computed from the nth derivative of the effective action, and the vertices are also computed in the same way. The convention that we use is that the vertex is the negative of the derivative, as shown in the green box at the bottom of your slide. And the vertices are, however, not just the physical vertices. After working out these vertices, we need to substitute, after working out the expressions for the vertices, including the j's, including the sources, external sources, we need to put the external sources equal to 0 to get the physical vertices and the propagators, and that therefore, the physical vertices and propagators that are relating to the field are given by the expressions in the red box at the bottom of the slide. And because dxy is the inverse of the 2-point function, we have the expression which is given in the red box at in this slide. So, this is an important caveat. As I mentioned, we need to include the sources when we do the workings, and after we get all the expressions including the sources j, we then put the sources j equal to 0 and then arrive at the contributions or arrive at the expressions for the propagators and the vertices. In other words, let me repeat, first of all we work out the expressions for these propagators and vertices in the presence of sources, then put the sources equal to 0 and arrive at the physical expressions for the propagators and the vertices. Now let us look at the derivation, skeletal derivation of the Schwinger-Dyson equation or Dyson-Schwinger equation. We start with a total derivative of the form which is given here in the red box. Obviously, this being a total derivative, it vanishes, and when we do this derivative as we have done earlier in the context of the 0-point field theory in 0 dimensions, field theory in 0 dimensions, the approach is almost exactly parallel. In fact, that was one of the advantages of studying field theory in 0 dimensions. The modus operandi is almost parallel exactly, although the calculations naturally become more cumbersome, more tedious. Anyway, so when you do this derivative, functional derivative with respect to phi, you get the expression within the curly bracket, and the rest of it remains as it is, and this gives us the expression which is given in the green box, which you recall coincides with the expression, similar expression which we obtained in the case of the zero dimensional field theory. Then we now substitute Zj with e to the power wj to obtain the expression for the wj, and we make use of this identity. This identity is quite straightforward. If you look at this, the functional derivative of jx, functional derivative with respect to jx of e to the power wj into an arbitrary function f, e to the power wj into an arbitrary function f is given by the expression given in the blue box here. When you simplify this expression, what we find is it can be written in the form that is in the green box here. When we simplify this whole expression, the e to the power minus wj cancels with e to the power wj, and that leads us to the expression given in the green box right at the bottom of your slide. So this is the expression that we had. This is the expression that we had for the generating function, the Schwinger-Dyson equation for the generating function, and this expression enables us to write the expression for the connected green function, generating function for the connected green functions in the form that is given in the green box at the bottom of your slide. This can be simplified further by writing it in the form, using this expression in the blue box that we have proved just now. Using this expression, we can write this expression for the connected green functions, or the generating functional for the connected green functions in the form given in the green box right at the bottom of your slide. Now, the Schwinger-Dyson equation for the connected green functions can be obtained by acting with further source derivatives on the above equation, and now we talk about the effective action. The effective action, as you know, is the Lagrange transformation of wj with respect to the source jx, and therefore we can write the functional derivative of wj with respect to jx as phi x, and the functional derivative with respect to jx can be written in the form that is here in the red box at the bottom of your slide. So this is established. The first part is quite straightforward, because the effective action is a Lagrange transformation of wj with respect to the source j. Therefore, the functional derivative of wj with respect to jx will return the effective the field function phi, and the proof for the second relationship is given in this slide, which the functional derivative with respect to jx can be written in the form given in the red box here right at the top of the slide, which can be simplified using the fact that the field function is the functional derivative of wj with respect to j. We use this expression for simplifying the field function capital phi of z, writing it as del wz upon del jz, and on simplification we get the expression that is in the green box right at the bottom of your slide. Therefore, the expression for the effective field or the effective action can then now be put in the form that is shown in the red box at the top of the slide. Red box at the top of the slide. Please recall that this effective field is the generating functional for the 1 pi from green functions, and these 1 pi green functions can be derived from this effective action by further differentiation. So now we come to the example of this 5-4 field, whatever we have done so far, but I will take it in the next class. Thank you.